Welcome back, students. So this is our last week of lectures. Wish you all a very happy Diwali. So we are going to move on to a new topic, which is feedback. So feedback is an integral part of our life. All of you must have experienced feedback throughout your childhood when you went through exams in your school and you did well or you did not do well, and you got a lot of feedback from your parents probably. And what does feedback really do? Feedback improves your performance, right? Similarly, we can take some real life examples. For example, imagine you couldn't hear what you're saying. Many of you may have used those headphones which are like, on top of your ear, specifically if you have any kind of noise cancellation headphones. And what you will quickly see is you cannot hear what you're talking. And if you try to sing a song, it will be totally off key. So feedback is necessary. We need to really hear what you're saying, what we are saying, and then we can adjust the frequency of our sound so that we are in tune. So that's one type of feedback, which is auditory feedback. The visual feedback we constantly use. If with your eyes you are able to sense where you're going, and you're able to avoid lots of things. So your brain is getting feedback from your eyes, and then you are modifying your actions. So feedback is important in circuits also. So far we have been looking at op-amp design, and now we are going to get into feedback. And we are going to see how to improve the performance of our circuits using feedback. So let's draw general feedback system, and it looks like this. Signs of this summation block are important. Sometimes you may make a mistake here and then you will get a wrong answer. So it's important that this input sign is positive and this is negative, indicating negative feedback. Okay. AS is the feed forward gain. S indicates that it's function of frequency, and beta is the feedback. In this case, we are assuming that it's constant over frequency. So it's like a scalar. So then we can write the expression here, beta times y of s, and this would be xs minus beta times y of s. That would be this particular output. So we can solve this equation. Beta is called feedback factor. If we solve this, we will get closed loop gain. That will be ys divided by x of s. That will be equal to as divided by 1 plus beta a of s. The terminology is important here. As I said, beta is the feedback factor, and ys divided by xs is the closed loop gain. And the term here in the denominator, beta times a of s, we call that T is equal to loop gain. Important to note that T loop gain is different from closed loop gain. Many people, many designers get confused between the two, so it's important at the beginning itself that you have this clear in your head. Now, if beta times a of s, for example, this part here in the denominator, let's pay attention to that. If beta times a of s is equal to T of s, the loop gain, if it is equal to minus 1, then what happens? We can immediately tell that, hey, this term will go to 0, as a result of which the closed loop gain will go to infinity. What this really means is you have very large output at ys, and the circuit is oscillating. That's what it means. So we get into a condition where without any input, we have very large output, and we call that Barkhousen criteria for oscillations. A of s and beta in the feedback plus minus summation. If a of s times beta, the phase shift here is 180 degrees, which is what is indicated by this. Then there is total 360 degree phase shift around the loop. The rest of the 180 degree comes in because of this subtraction over here. And then what happens is that the signal will add constructively around the loop, causing oscillations. For example, when I'm in the classroom, I'm using a microphone and that sound is getting amplified and it's coming out of speakers with certain amount of amplification. If I move along with that microphone close to the speaker, then what you will definitely notice is a loud pitch tone. We call that a positive feedback. The reason we call it positive feedback because we have 180 degrees and yet another 180 degrees because of the inversion, as a result of which we have oscillations. So in general, when we are designing the amplifier, we would like them to be stable. We really do not want them to oscillate unless we are trying to design an oscillator where we intentionally want this particular phenomenon to happen so that our circuits can oscillate. That part we are not going to cover in this class. So we will focus on making sure that we design our amplifiers which are stable and they do not oscillate. Let me give you an example of a feedback with a circuit. In this particular case, this particular block, generally we have used this for op-amp designs very early on in our classes. The A of S represents an op-amp with a large gain, and this particular part here is the beta, representing beta. So this is beta in this case. Let's say this is R1 and R2. Then beta would be R2 divided by R1 plus R2. This comes in purely as a voltage divider. If we look at our original definition of feedback, we can compare this particular schematic to that, which is right over here. We can see that the feedback factor here is beta, which is R2 divided by R1 plus R2. Now, what is the loop gain in this particular case? The loop gain, as we can see, will be equal to A times beta. So in this case, it would be A times R2 divided by R1 plus R2. Now let's find out what's our closed loop gain going to be. A divided by 1 plus A beta. And in this particular case, beta is R2 divided by R1 plus R2. So that would be our loop gain. Let's examine this particular circuit carefully. What if R2 goes to infinity? So in this case, if R2 goes to infinity, we can modify this transfer function as Ys divided of x of s is equal to A divided by 1 plus A and 1 divided by R1 divided by R2 plus 1. Now this makes it easy. When R2 goes to infinity, this particular term in this case will go to 0. And we will get Ys divided by x of s will be equal to A divided by 1 plus A, and that will be equal to 1 because we know A is very large. And if we draw the circuit that we are used to, it's going to look like this. If we are saying that R2 is infinity, so the circuit is going to look like this, and this is nothing but our unity gain amplifier. This resistance doesn't do anything because there is no current flowing through that resistance, and this is equivalent to what we have learned earlier, which is this plus minus x of s and y of s. What are the advantages of feedback? We're going to get deeper into this topic step by step, and I'm going to explain each one of them to you. So the first, let's summarize all the advantages and disadvantages, and then we will convince ourselves that this is what is really going on. As I told you earlier, feedback improves your performance. So our expectation is that the feedback is going to improve the performance of our circuits. So the first thing we say is gain desensitization. We're going to go through each one of them with examples of each one of these. The next thing is feedback modifies terminal impedances. Third one is bandwidth modification. Specifically, feedback will improve your bandwidth. And the fourth one is nonlinearity reduction. I'm going to go through each one of these. And the disadvantages of feedback, you should know. There are two of them. One is gain reduction, and the second one is you have to worry about stability, and we will write that as potential for instability. As we already saw, by making beta AS equal to -1, we are going to get an unstable system which will start oscillating. Let's go through the first one, gain desensitization. Let me give you an example. So we already said closed loop gain is ys divided by x of s is equal to as divided by 1 plus beta times as, and that is equal to a divided by 1 plus r2 divided by r1 plus r2 times as. Now if a is very large, then a times r2 divided by r1 plus r2, that is also very large, greater than 1. We are assuming r1 and r2 are practical values. Then we can rewrite this expression as a divided by r2 divided by r1 plus r2 times a, and that is approximately equal to 1 plus r1 divided by r2. So far what we have been learning about is design of an operational amplifier A, and in that case we were saying our gain is given by expressions like GMR out or GMR out square if you have a two-stage operational amplifier. So that number is quite large. It could be 1,000, 10,000, a million, depending upon how you design it. So with such a large gain, and if you put feedback around it, you get effective transfer function as 1 plus R1 divided by R2. Now on a chip or in an integrated circuit, when you implement R1 and R2, we can choose a certain ratio by making unit cells for both R1 and R2. For example, let's say if we choose R1 divided by R2 equal to 4. So R1 divided by R2 is equal to 4. So we will make R1 using 4 units of R2 in series. So R1 is made using 4 units of, let's say this is R2, 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 and R2. And we have R2. These resistors are on the same chip right next to each other. They match very well with each other. So we get this ratio of factor of 4 fairly accurate. And we get this, for example, in this case, we will get a gain of 1 plus 4, which is equal to 5. This will be very accurate. Just because these resistors are made using unit cells and they are next to each other and they matched very well with each other. So we get accurate gain, which is independent of this factor of 5 is only dependent on how well the resistors match with each other. It will become independent of GM, R out, purely because the gain A is very large. It can move around a little bit, even as much as 50% of a large number. But even then, our effective gain will be 1 plus R1 divided by R2, and R1 divided by R2 will be factor of 4 by design because all the resistors are on the same chip right next to each other, made using identical components. So this is what we mean by gain desensitization using feedback. The next thing we're going to talk about is bandwidth modification. So let's assume that our transfer function A of s is given by A0 divided by 1 plus s divided by omega p1. So A0 is a DC gain, large DC gain, and omega p1 is the pole location, where at the pole location A of s will drop to by 3 dB, if you remember the Bode plots that we did. Now if we substitute this in our loop gain T of s, then we will get that's equal to beta times A0 divided by 1 plus s divided by omega p1. And our closed loop gain will look like ys divided by x of s. You can write it on your own. You can substitute in our expression, which is A of s divided by 1 plus beta A of s. So I'll wait here till you substitute and come back with a simplified expression. So you can prove it to yourself that the new closed loop gain looks like this is our closed loop gain. After substitution is going to look like A0 divided by 1 plus A0 beta divided by 1 plus S divided by omega P1 1 plus A0 beta. So here you can see our DC gain is desensitized, and if A0 is large, then this will approximately look like 1 over beta. And our new pole location right here, this is the new pole location. If you compare it to this expression, you will immediately see that that's the new pole location is omega P1 1 plus A0 times beta. And we already said that for practical values of beta, A0 beta is very large. So omega p1, which was the original pole location, now has become omega p1 times 1 plus a beta. So this is large. So we say that we got increase in bandwidth because of feedback. Our original bandwidth was omega p1. Now we have a new bandwidth, which is omega p1 times 1 plus a0 beta. So let me draw this graphically, and then it will become very clear how the bandwidth increases. So the yellow curve is our original transfer function, which is A of S, open loop transfer function, divided by 1 plus S divided by omega P1. And this is when beta equal to 0, for example. And the magenta curve, what you're seeing here, is the closed loop gain. And in this case, let's say beta is equal to 0.5. So this would look like, for example, this would look like 2 log of 2, 20. So this would look like 6 dB for that matter. The original omega P1, which is right here, and here is the new, which will be equal to 0.5 times A0 omega P1. And if you remember, I think in first or second or third lecture, we had done unity gain frequency response. And there we said that it was the gain bandwidth product, which is right over here, which is A0 times omega P1. So we can see clearly from this example that we went from bandwidth of omega P1, which is right here, to all the way beta times A0 times omega P1 over here, increase in the bandwidth from omega P1 to A0 beta omega P1 approximately, assuming A0 beta is very large. In this particular case, we said its beta is 0.5. If we take a beta of 0.5, then we will get the magenta curve will intersect the y-axis at 6 dB, and we will have half the unity gain bandwidth of original AS. This half is the beta factor. Remember on this case, I forgot to explain in the beginning, when we are plotting this, just a refresher, we are plotting frequency on the log scale and gain in the dB scale. This is something that we have learned how to do it when we are doing the Bode plots. Next, we will look at an example of impedance modification. So feedback modifies input and output terminal impedances. They can go up or down, and it all depends on the circuit configuration. So let's start with one example. And initially, we are going to do some brute force analysis, which means that we'll just do KCL, KVL, etc. And then we will come up with a bunch of rules in the next lecture where you can, by inspection, tell what's going to happen. So we're going to study different types of feedbacks in the next lecture and associated rules about impedance modifications for each feed. So let's take an example. You can start drawing the schematic along with me. Now we would like to format this circuit for what we are used to seeing for feedback analysis, which is specifically this way. And I'll show you how to do that. A of S and beta, okay, V in plus minus, and we will compare to that one. So in this case, let's just do correspondence. A is represented by our transistor M1 and RD, and beta is represented by R1 and R2. Okay. Now in this case, we are applying a voltage which is VGS, and on one side of the one side we are applying the beta times V out, and on other side we are applying to the source. So the VGS part acts like a subtractor. Okay. So the M1 VGS acts as a sigma plus minus block that we're used to. Now to analyze feedback, first what we do is we break the feedback loop over here. So we will break the feedback loop over here, and let's see what is we will start analyzing each element. So once you break the feedback loop, this is what our circuit is going to look like. Okay, this is V out, and this is RD, V bias, and this is V in. Now we have done this circuit before. This is a common gate amplifier, and we know that the gain is of this amplifier A0 is equal to GM times RD, and our beta is R2 divided by R1 plus R2. In this particular case, we are going to assume that the feedback part, which is right here, is the resistors R1 and R2 are much larger compared to RD, so that the feedback part doesn't really load our the open loop gain, which is GMRD. Now let's figure out what is R in and R out before the feedback. Then our R in, which is looking in here, we know that is equal to 1 divided by GM of the transistor. And the R out at this point is given by RD. Here we are ignoring the channel length modulation for M1. And also the assumption is beta doesn't load our output, which means that R1 plus R2 is large. So these are called open loop impedances. Now let's see what happens after we close the loop. And for that analysis, as I said, we are going to do brute force analysis, which means we're just going to solve KCL, KVL. And you can do that yourself. I will just do the small signal model first, and then you can solve the equations. On the right side, I'm going to draw the small signal model. Since we are looking for R in, which is the resistance looking into this node, after feedback, we are just going to apply a test voltage called Vx and look at the current Ix, which is going to flow into that node. And Vx divided by Ix will give us the R in of the circuit with the feedback. So you can draw the small signal model on the right side. So one more approximation we are going to do is, since I already said R1 and R2 are large, we can assume that they are not really taking any current out of this output node. So the assumption is that the current Ix will completely go through RD. Again, this is an approximation to get a quick answer. So we are saying the current Ix is going to flow through this, and we will get voltage at this point will be Ix times RD. The reason for this assumption is R1 plus R2 is much greater than RD. And what this means is that the feedback network is not loading our original network. If it does, then we have to take that into account and it will modify all our equations. But for the first order analysis, we can assume this so that we can draw some insights. So we can write the first expression, Ix is equal to the voltage at the resistive divider, R1 and R2 is going to be R1, R2 divided by R1 plus R2 times Ix times RD. And our current source value here, that is going to be GM times VGS. And what is VGS? G is this particular voltage, okay, which is R2 divided by R1 plus R2 times Ix RD. And what is S? S is Vx minus Vx. So Ix is equal to Gm times Ix RD, R2 divided by R1 plus R2 minus Vx. Okay, so you can rearrange the terms and you'll see Vx divided by Ix is equal to 1 over Gm times 1 plus R2 divided by R1 plus R2 times Gm RD. Now here is the interesting part. This 1 over Gm was our open loop Rin, and this is our beta, and this is our A of S. Okay. So closed loop resistance or closed loop impedance is equal to open loop Rin multiplied by 1 plus A times beta. Again, this is large. So in this particular example, our input impedance has increased by factor 1 plus A beta. Similarly, I would like you to prove as part of your homework that closed loop resistance or closed loop impedance, output impedance, what would you do for closed loop output impedance calculation? You would apply a test voltage at the output and you will do KCL, KVL and find out what is the current flowing into that node just by doing similar analysis. And while you do that, of course, the input you will have to ground it because it's a voltage source. And what you will see that the closed loop R out will be equal to open loop R out. In this case, it would be RD. That's what we determined in the beginning. And that will be divided by 1 plus A beta. So you can prove it to yourself by doing this same math analysis. Next thing we're going to talk about is linearity improvement. So this red curve is our open loop gain, the original transfer function A. And as you can see, the gain is very high. And after feedback, we get this particular characteristics, which looks like something like this. So this is your A, and this would be your A divided by 1 plus A beta. So the linearity corresponds to the curvature of the transfer function at any point. So for example, if I have a straight line versus if I have some kind of curved line, right? So this definitely is not linear, but you could say that this looks like a straight line, so it's linear. What feedback really does is reduces the dependence on nonlinear A. So feedback factor beta, we generally achieve using ratio of resistors or capacitors. So these are elements which are very linear compared to active devices. So when we talk about closed loop gain, we get A divided by 1 plus A beta, and we can rewrite that as A divided by A beta 1 plus 1 divided by A beta, and then we can say that this is equal to 1 divided by beta 1 plus 1 divided by A beta, and as A beta is very large, 1 divided by A beta is very small, so I can write this as 1 divided by beta and 1 minus 1 divided by A beta as an approximation. So we can see that 1 divided by A beta is really small. So the overall closed loop gain is closely resembling 1 divided by beta with very small dependence on A. So A varies a lot because A is implemented using transistors and they can be nonlinear. But beta is implemented using ratio of resistors or ratio of capacitors, and they are very linear. So overall effect after closing the loop using feedback is we get higher linearity. Before we move on to our next topic, I would like to define 4 different types of amplifiers. First one you already know, which is a voltage amplifier. So these are 4 types of amplifiers. First one is a voltage amplifier, and in this case we have gain A 0. This is V in and V out. V out is with respect to the ground. So in this case we would like to see R in is equal to infinite because we don't want any current to flow in here, I equal to 0. And what would we like to see R out? We would like to see that as a 0. So realistic model of the amplifier is going to look like this. This is V in and this is your R in, and we have plus minus A0 times V in and we have R out. And this we have done before many times, right? So this is the realistic model of the amplifier, voltage amplifier. Next amplifier we're going to talk about is a transconductance amplifier. So in the voltage amplifier we had input voltage and output voltage. So in the transconductance amplifier, so we have input voltage. So since input is voltage, we would like to see Rin equal to infinity. And we have output current, which is I out. So we would like to see here, since it's a current source, we would like to see R out equal to infinity also. And the model, the realistic model of this is going to look like this. We have seen this before when we talked about MOSFET transistors, right? MOSFET transistor looks like a transconductance where we have R in, which is infinity, and R out, we would like to have it as high as possible. The third amplifier we're going to look at is called Transimpedance Amplifier. And let's look at how we represent this. So in the Transimpedance Amplifier, or in this particular case, Transresistance Amplifier, we have current input and voltage output. Since it's current input, we would like to see Rin equal to 0, so that all the current goes inside the amplifier, and its voltage output, so we want Rout equal to 0. Okay, and the realistic model Rm is going to look like this. So we would like to see ideally Rn equal to 0 and Rout equal to 0 because it's a voltage output, and this represents your realistic model. The last configuration, current amplifier, and in this case we have current in and current out, I in and I out, and this is your current gain AI. So in this case what we would like to see is Rin equal to 0, but Rout should be equal to infinity. Because output is a current source, so we would like to see very high output impedance. And the realistic model will look like this. In, Rin, and here is our output current source, AI times In, and here is our Rout. And this would be I out. This is the realistic model for current amplifier. Now feedback has different effect on each one of these amplifiers. And in the next lecture, we are going to start looking at feedback associated with each one of these amplifiers.